One of the biggest problems with Einstein's general theory of relativity comes with the question about the origin of the matter in Einstein's theory. His famous equation contains an addend which cannot be derived, but had to be postulated. It is a matter term. Interestingly, without this matter term, Einstein's field equations reduced to the so-called vacuum field equations, because, as it says, they would not consider or contain any matter. But is this correct? And if yes, where could we find a truly metric origin for Einstein's matter? A theory of everything, for which we are aiming here, should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In this talk, apart from the derivation of Einstein's field equations, we will mainly concentrate on the latter aspect. Already in 1915, it was the great German mathematician David Hilbert who derived Einstein's field equations from a fundamental minimum principle. His only problem was that he, too, could not give a proper origin for the matter term in Einstein's equation, but, like Einstein, had to postulate it. For this, he introduced the matter density Lm. When following Hilbert's derivation and setting the matter term and the cosmological constant to zero, namely, one does not only result in a rather simple variational integral, which kernel, surprisingly, consists of not more than a term describing the curvature of space-time, but one also only ends up with the Einstein field equations for the vacuum and thus matter-free case. Apparently, at least this was Hilbert's and Einstein's conclusion. Matter needs to be artificially brought into the derivation in order to make sure that in the end it is in the theory at all. Here we will now show that this assumption was wrong. Here we will show that Hilbert's and Einstein's approach apparently was complete, but that they had little chance, as being too far ahead for their time, to see it. We start with a simple scaling factor of our metric tensor. As it can be shown, this f of f also appears to be the wave function within our metric description, but this aspect shall be the topic for our next presentation within this series. The important point we are interested in here is that, by introducing this factor, the new Einstein vacuum field equations suddenly appear with an additional addend. An addend which clearly has the markings of the long-sought matter term. The interested reader can find the complete evaluation with a lot of additional options in the presentations given below and quite some other papers or books by this author. Here, we will only briefly consider one of the simplest paths. At first, we consider the variation our simple scaling or wrapper function does to the Einstein-Hilbert action and obtain the following new and rather complex variational integral. But even though it looks a bit complicated on first sight, the thing can be evaluated. Along the way, we realize that there are options to split up the integrand, and as we do not see why the universe, probably also seeing such degrees of freedom when looking for a minimum in its own existence, would not seize such a chance and use it. We suddenly result in a huge, if not to say infinite number of possibilities for our simple wrapper approach with respect to forms of potential matter. When finishing the Hilbert calculation, namely, we clearly end up with the non-vacuum Einstein field equations, only that this time we had not slipped in the matter in any artificial way, but we saw it popping out of the Hilbert calculus by its own. We conclude that matter does not need to be postulated, but just consists of forms of volumetric variations of space-time or similar scaling options. Here we only presented the simplest option, for such an extension of the classical Einstein-Hilbert action, but there are more, many more possibilities. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out here, however, that we do not consider us the first to have found the connection. In principle, namely, it all was already inside Hilbert's ingenious approach, and he only could not see it because, at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and his main goal was the derivation of the Einstein field equations, and thus, as Einstein had postulated the matter, Hilbert, as a mathematician, obviously did not bother about doing what he probably considered the physicist's job, namely the derivation of the origin of that matter. Just for completeness, it should be mentioned that one option to obtain even more complex matter forms, including fermions, can be obtained by avoiding the condition for the scaling function f we had introduced at the beginning. We had done this only in order to keep things brief and simple. Again, the interested reader finds the complete evaluation in one of our books. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? The optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. A next, smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via a working quantum gravity computer tech. Everything else are service projects.